All right, today we're talking about water. This is the last part of your basic food chemistry notes, and you should have your notes template to fill in. So it should look something like this: basic food chemistry, water. We got a few things to fill in. All right, let's start with water in our bodies, right? So there are several functions of water in your body. One of them is to maintain your body temperature. Water has a really high specific heat, and that means that it takes a lot of energy to change the temperature of water. Other substances like rubbing alcohol or something, they can change temperature really quickly. And so life on this planet and assuming life on other planets is all water based, meaning that water is really good at maintaining body temperature. Sweating is something that we do to release heat, right? So then when the sweat evaporates off of your body, it takes that heat with it. So water is really important for maintaining temperature. It's also really important for transporting nutrients and waste. So your blood, very liquidy, right? Mostly water, urine. So when you are going to the bathroom frequently, you're flushing out a lot of those things that need to be transported out of your body. And then also, obviously, your blood transporting nutrients throughout your body. Your metabolism. So if you remember anything about dehydration, synthesis, and hydrolysis, you hear the word hydration and hydro in both of those words. Dehydration synthesis means to build materials, to synthesize. And when you build materials, water is released in that process. But hydrolysis means to break materials, and water is used to break down. So if you are eating food, you oftentimes get thirsty when you're eating because your body needs that water to be able to digest and break down those food molecules. And then water is a major component of our body tissues. So a lot of times people think that people are about 75% water, and that might be true for babies. They're very squishy, but as an adult, we are more about 60% water. But still, that's a lot of water in our cells. If you are feeling thirsty, that means that you're already dehydrated. So proper hydration means that you shouldn't feel thirst if you are already consuming enough water. So how many ounces of water should you consume every day to stay hydrated? Well, if you take your body weight, you divide it by 2, that's how many ounces of water you should have. Now, again, it kind of depends on what you're doing. If you are sweating a lot, if you're exercising a lot, you should probably up that number. But just in general, to stay fully hydrated, if you weigh 200 pounds, then you should be consuming 100 ounces of water every day. Okay. They say that cold water will hydrate you faster than warm water. And the explanation for this is that cold water causes your stomach to constrict, which would actually be like squeezing a sponge, forcing the water out into your bloodstream at a faster rate. I'm not sure how much of that is true, but that's what they say. What about sports drinks in terms of staying hydrated? Well, sports drinks can be good if you're physically active for more than an hour. A lot of sports drinks have sugar in them. You don't want one that's really high in sugar, but a small amount of sugar will provide the energy for the activity. So it'll replace your glucose. It'll replace usually the sodium and the potassium that has been lost through sweat. The sodium also helps your body to retain fluid, so to hold on to that extra fluid. Gatorade was one of the original sports drinks, and the quick story behind this is that the Florida Gators, the University of Florida, they had a sports trainer that created this concoction of balance of sodium and potassium and sugar and things, and he would give that to the Gators, the Florida Gators football team, to replenish their electrolytes and hydrate them or whatever. So they named it Gatorade to aid the Florida Gators. And that's been kind of the thing ever since then. When it comes to best electrolyte drinks for replenishing, there is a link there that you can click on if you want to, or go to that link. But basically, one of the best things for rehydration is Pedialyte. If you were ever sick as a kid and maybe your parents gave you Pedialyte popsicles or Pedialyte drinks, that's actually the best one for rehydration. But you can see I've got things like Liquid IV on here, coconut water, there's Drip Drop, there's different rehydration technologies, let's say. But again, if you're not like overly exercising and sweating and stuff, just regular water is totally fine. One of the things we're going to talk about in a minute is altitude. If you are living in a higher altitude above sea level, more water actually evaporates from your skin and from your breath when you're talking because of the lower atmospheric pressure. So I'm going to circle back to that in a minute. But people that have high altitude jobs, so pilots, flight attendants, or even the Denver Broncos, Denver's known as the Mile High City, it has a high altitude. They need to be aware of their altitude and how much more water they are expelling, even just by talking, existing. And so their water consumption would probably be more than what we would need here in Ohio. Okay, we did the properties of water. So you should know H2O is the chemical structure of water. It's got 2 hydrogens, right, and an oxygen. And the overall charge of water is neutral, right? It's got the same number of protons and electrons. However, most of those electrons are being held on the oxygen side. And since electrons have a negative charge, that tends to be the slightly negative side of water, which means that the hydrogen side is slightly positive, and it gives water that bent structure. And so because it has a positive and negative region, we say that water is polar. It has poles or sides to it. That polarity is what allows water to combine and be attracted to other polar molecules. So like with like, water likes other water molecules like the magnets, but water will also be attracted to other slightly positive and negative things. And that's what makes water such a good solvent. So in this picture here, let's say you plunk some sugar into a glass of water. Well, when you take a closer look at these glucose molecules, you see these slightly positive and negative regions that water will be attracted to. And so when we did our activity in class, we had the sodium and chloride. So the sodium has a positive charge, the chloride has a negative charge. So water is attracted to those molecules. Now remember, the oxygen is slightly negative, so that's why it's oriented toward the positive, the sodium. The hydrogens are slightly positive, so they're oriented toward the negatively charged chloride. But that's how water dissolves substances. So something like fat, oil, those are nonpolar. There's nothing for water to be attracted to dissolve it, and that's why oil and water don't mix. It's just chemistry. Okay. All right, so the temperature, pressure, phase changes. When it comes to pressure at sea level, we say that standard atmospheric pressure is 1 atmosphere. And when you go above sea level, like Denver, I said, is known as the Mile High City, there's less pressure there. So it's 0.83 atmospheres versus something like Death Valley, which is below sea level, and there is higher pressure there, 1.01. So when you look at this picture, it's basically saying like, the closer you are to the ground, the more molecules and pressure there is on your body, right? But as you travel up higher into the atmosphere, there's less pressure on your body, which means that water can escape faster, easier. It can come out of your body. Which is then what we're going to relate to boiling points. So what do we typically say is the temperature that water boils, right? 100 degrees Celsius. That's what we say, or 212 Fahrenheit. But when you go into higher altitude, there's less pressure pushing down on that water. So molecules already can phase change a lot easier. Molecules need less energy when there's less pressure pushing down on them. So if you travel up to the top of Mount McKinley, water will begin to boil at 78 degrees Celsius. Now that's not really hot. Like if you were to touch that, it wouldn't be like super hot. It'd be like bath water, right? But it would be physically boiling. So it's kind of weird. It's like the water is boiling, but it's not as hot as you would think. Now, if you go below sea level, all right, there's more pressure pushing down. And so there's more energy that's needed or higher temperature to get that water to actually phase change. So when you look at this sort of side by side, right, if you start at sea level, right in the middle, 100 degrees Celsius is what we typically think of as that's the temperature that water boils, or 0 degrees Celsius is the temperature that water freezes. However, when you actually change your location in altitude, it can impact the ability of water to boil or freeze. So at the top of Mount Everest, again, water will boil at about 70 degrees Celsius. That's like not that hot. I mean, it's not hot boiling like what we would think, right? But at the Dead Sea, you have to raise the temperature above 100 degrees to get it to actually boil. So how does this impact cooking? There was actually a Top Chef episode for anybody that watches the Top Chef where one of the challenges was that they were up in, I don't remember exactly where, but like this little picture here is from Colorado State University. So Denver, Colorado, obviously high altitude up into the mountains. There are like ski resorts and stuff like that where chefs have to accommodate for the change in altitude to be able to cook food properly. And so there are some things to be aware of when you are doing high altitude baking, for example, right? So because water boils at a lower temperature, food will actually take longer to cook in boiling water. So like if you put pasta in a lower temperature and you're waiting and waiting and waiting, okay, the food that's cooked at these lower temperatures will actually begin to dissolve before it even cooks. So pasta can come out sticky and mushy. Again, if you're a chef working in one of these ski resorts or something, you have to be aware of that so that you can adjust your cooking times and temperatures and stuff. If you are baking, right? Remember, as you go up in altitude, there's less pressure on you. So that means your batter, your muffins will rise a lot easier, right? They will rise higher. So if you don't accommodate for that, your product can be dried out. It can lose a lot of that moisture. It can have a coarse texture. Maybe it even collapses because it rose too quickly. Again, because things phase change at lower temperatures, cakes can be underdone if you don't cook them longer than the standard recipe calls for. So they may be sitting in that oven going. The recipe called for 20 minutes and your cake still isn't done yet. I already mentioned that water evaporates faster at higher altitudes, so it can dry out your products a lot easier. There's a couple of trial and error things, and you can look up stuff if you're interested, but basically they say one of the things to try is to use up to 20% more water than the standard recipe might call for. You could add 5% more flour because that's going to slow down the leavening process, right? Because leavening is what causes that rise. You don't want it to rise as much at higher altitude. Or reduce your leavening agent by 60%, so if it's calling for a certain amount of baking soda or baking powder, really cut back on that. And most recipes might say modifications to do for adjusting for certain altitudes. So again, if you look over at this picture here, it says for cakes, quick breads, and muffins, they give you the different altitudes and they give you what you should decrease or add, for each cup of flour, add more flour. For each cup of liquid, add this much more liquid because of all of these things that impact your temperatures and pressures and cooking times. So one last thing here, we can use this science and this physics to create or use what we call a pressure cooker. So the pot, as you can see in the image here, contains this seal that is steam tight. So as the steam, as it cooks, right, and as the water begins to boil on the inside, steam forms in the inside, but it can't escape. And so pressure begins to build. So when there's more pressure, that means more energy is needed for the water to boil. That means that your water can get to a higher temperature, right? Therefore, the food inside the pressure cooker will cook even faster. So as you can see in this picture, what they're doing is releasing the steam valve, and they put an egg on top to demonstrate the power of that steam. Now, pressure cookers can be a little bit dangerous if you don't know what you're doing, because if you open the lid without releasing that steam, it can explode, and steam exploding on your face would hurt a lot. So got to be really careful about that. But to put this into perspective, if you had a 3-pound pot roast and you cooked it at standard pressure, right? So around here, and you put it in the oven or whatever, it would take about 2 to 3 hours for it to cook through. But if you put that same pot roast into a pressure cooker, right, and there's, let's say, 15 pounds of pressure on the inside, that pot roast would be done in about 45 minutes, right? So we can use the science and the physics of pressure and temperature and all of those things to our advantage to make things go faster. All right, that's the end of these notes. Don't forget to do your Ed puzzle about boiling water, and that's it for today.